The silence. Go outside tonight, if you can. Find a place away from the city lights, a field, a hillside, a beach, somewhere the sky is dark enough that you can see the stars properly. Let your eyes adjust. Give it 10 minutes, 15, until the faint stars appear that the city never shows you. Now look. What you are seeing is the light of other suns. Not one other sun, thousands. Tens of thousands, visible to the naked eye on a clear night, and behind those, the faint smear of the Milky Way, which is itself 100 billion more. Each one a star. Many of them older than our own. Many of them with planets. Many of those planets in the zone of temperature and chemistry where liquid water can exist, where the reactions that produce life, as far as we understand them, can proceed. The universe visible to you from that field or hillside or beach is approximately 13.8 billion years old. The Milky Way alone contains somewhere between 100 and 400 billion stars. The observable universe contains, by current estimates, at least 2 trillion galaxies. 2 trillion galaxies. Each one containing hundreds of billions of stars. Each one having had billions of years in which life could have arisen, developed intelligence, built civilization, spread. By any reasonable calculation, any calculation that takes these numbers seriously and applies to them what we know about chemistry, biology, and the apparent abundance of planets, we should not be alone. We should be in a universe teeming with life, crowded with intelligence, loud with signals from civilizations that have had billions of years longer than we have to develop and transmit. We hear nothing. This is the problem. It has a name, the Fermi Paradox, and it has been one of the most seriously discussed puzzles in science and philosophy for 70 years. And it has not been solved. Tonight, I want to sit with this silence. Not to give you false comfort, not to provide a tidy resolution, but to really feel the weight of it, the weight of a universe that is vast and old and, as far as we can determine, completely empty of anyone but us. And then I want to take you through the attempts to explain it. Because the explanations that have been proposed are, in their variety and their implications, some of the most consequential ideas that human beings have ever entertained. The Fermi Paradox takes its name from Enrico Fermi, one of the most important physicists of the 20th century, the man who built the first nuclear reactor, who contributed centrally to the development of the atomic bomb, who won the Nobel Prize in 1938. In the summer of 1950, Fermi was at Los Alamos, the New Mexico laboratory that had been the center of American nuclear weapons development during the Second World War and remained a center of physics research afterward. He was having lunch with colleagues, the physicist Emil Konopinski, the physicist Edward Teller, and the physicist Herbert York, and they were discussing a recent New Yorker cartoon about flying saucers. At some point in the lunch conversation, Fermi asked, apparently in reference to the absence of evidence for extraterrestrial visitors, "Where is everybody?" The question was asked casually, in the context of a lunch conversation, and the specific words have been variously reported by the people who were present. But the essence of the question is clear, given the age and size of the universe, given the apparent abundance of the conditions for life, given the amount of time that intelligent civilizations elsewhere would have had to develop and spread, where are they? Why haven't we heard from them? Why haven't they arrived? The question stuck. It was remembered by those who had been present, discussed in subsequent years, and eventually codified as the Fermi Paradox, the contradiction between the expectation, from the numbers alone, that we should be surrounded by evidence of other intelligent life, and the observation that we have found no such evidence at all. Fermi himself did not develop the paradox extensively. He died in 1954, for years after the lunch, of stomach cancer. but the question he had asked casually over a meal has outlasted everything else, has generated decades of scientific and philosophical discussion, and remains, 70 years later, unanswered. In 1961, 11 years after Fermi's lunch question, a young astronomer named Frank Drake attempted to formalize the reasoning behind the paradox, to make explicit the calculation that produces the expectation of abundant extraterrestrial life. Drake was organizing the first scientific meeting devoted to the search for extraterrestrial intelligence, held at the National Radio Astronomy Observatory in Green Bank, West Virginia. To frame the discussion, he wrote on a blackboard a series of factors whose product, he argued, would give the number of communicating civilizations in the Milky Way galaxy at any given time. The equation he wrote, which became known as the Drake equation, multiplies together the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets that are in habitable zones, the fraction of habitable planets on which life actually arises, the fraction of those on which intelligence arises, the fraction of intelligent species that develop communicating technology, and the average length of time such civilizations remain detectable. The equation is not really an equation in the mathematical sense, it is a framework for thinking about the problem, a way of identifying the variables that matter and exposing where our uncertainty lies. The individual factors are largely unknown, which means that estimates of the final product, the number of communicating civilizations, vary wildly, from less than 1 to hundreds of millions. What the Drake equation does, even with this uncertainty, is make explicit the reasoning that underlies the expectation of abundant life. If even a small fraction of stars have habitable planets, and if even a small fraction of habitable planets produce life, and if even a small fraction of life-bearing planets produce intelligence, and these are small fractions of very large numbers, the result is still many, many civilizations. And we have detected none of them. To understand the weight of the Fermi paradox, you need to understand not just the size of the universe but its age. The universe is 13.8 billion years old. Our solar system formed approximately 4.6 billion years ago, which means that the universe had already been running for 9 billion years before our sun ignited. In those 9 billion years, countless generations of stars were born and died, seeding the galaxy with the heavy elements that make complex chemistry possible. Countless planets formed. Countless opportunities for life existed. An intelligent civilization that arose on a planet around a star that formed, say, 8 billion years ago, 3.5 billion years before our sun, would have had 3.5 billion more years than we have had to develop, to spread, to build. 3.5 billion years of technology. 3.5 billion years of expansion. Consider what our civilization has accomplished in the last 3,000 years. Now imagine 3.5 billion years of that trajectory. Even at the most modest rates of technological development and expansion, a civilization with that head start should be visible across the galaxy. It should have left traces, megastructures, modified stars, engineered planets, that our telescopes should be able to see. We see nothing. This is what makes the silence so profound. It is not the silence of a young universe, a universe that has not had time to produce life elsewhere. It is the silence of a very old universe, a universe that has had billions of years in which life could have arisen and spread and made itself known. The silence is not absence of time. It is absence of evidence. We have not been passive in the face of the silence. For more than 60 years, scientists have been actively searching for signals from extraterrestrial civilizations, an effort known as SETI, the search for extraterrestrial intelligence. The search has been conducted primarily through radio astronomy, scanning the sky for radio signals at frequencies that would be easy for a technological civilization to produce and that travel efficiently through space. The logic is that if another civilization wanted to make its presence known, radio transmission would be an obvious method. Over 6 decades of searching, we have detected one signal of interest, the WOW signal of 1977, which we have explored in another episode of this channel. The WOW signal matched the expected characteristics of an extraterrestrial transmission and has never been explained, but it has also never been detected again. Everything else, the decades of scanning, the millions of frequency channels monitored, the terabytes of data analyzed, has produced nothing unambiguously artificial. The sky is quiet. More recently, astronomers have been searching for evidence of advanced civilizations in other ways, looking for infrared signatures that might indicate a civilization capturing its star's energy on a large scale, looking for laser pulses that might indicate optical communication, looking for modifications to stellar spectra that might indicate industrial activity. These searches have found nothing definitive. Some anomalous signals have been detected and investigated, none have been confirmed as artificial. The silence is not from lack of looking. The absence of detected signals does not prove the absence of extraterrestrial civilizations. This distinction between absence of evidence and evidence of absence is important and often misunderstood. Our searches have covered a small fraction of the sky, a small range of frequencies, a small range of signal types, and a tiny fraction of the galaxy's age. An absence of detected signals in this limited search does not rule out the existence of civilizations that use different communication methods, that exist in parts of the sky we haven't searched, that existed before we started looking, or that are present but not transmitting in our direction. This is one of the possible responses to the Fermi Paradox, that the search has simply not been adequate yet, that we are looking in the wrong ways or the wrong places. It is a reasonable response, and it underpins the continued funding and expansion of SETI efforts. But it does not fully dissolve the paradox. Because the paradox is not only about signals. It is also about physical presence. A sufficiently advanced civilization, given billions of years, should have spread physically across the galaxy, sending probes, colonizing planets, building structures that would be visible at interstellar distances. We see no evidence of any of this either. The galaxy is not just radio quiet. It appears, as far as we can tell, to be physically empty of anyone but us. Why does the Fermi Paradox matter? It matters, first, as a genuine scientific puzzle, one of the most significant open questions in astronomy and astrobiology. The answer, when it comes, will tell us something fundamental about the nature of life in the universe and about our own place in it. But it matters in a deeper way too. The possible answers to the Fermi Paradox are not all equally comfortable. Some of them have implications for the future of our own civilization that are deeply unsettling. The same reasoning that asks where are the others also asks what happened to the others, and the answer to that question may be directly relevant to what will happen to us. This is the dimension of the Fermi Paradox that keeps some scientists awake at night, not just the puzzle of the silence, but the implication that the silence might be telling us something about our own fate. We will come to that. But first, we need to understand the proposed solutions, the full range of attempts to explain why the universe appears to be empty. The stars are still there. 2 trillion galaxies. Hundreds of billions of stars in each one. Billions of years of time in which life could have arisen, developed, spread. And silence. In Part 2, we go through the mathematics more carefully, through what we actually know about the conditions for life, about how common planets are, about what the numbers actually say. Rest here. Let the silence settle around you. The universe is very large. And very quiet. The mathematics of contact. Let me try to make the paradox concrete. Not with the full Drake equation, with its multiple unknown factors. That exercise tends to produce more uncertainty than clarity. Let me instead build up the reasoning from what we actually know, from the empirical facts about the universe that have been established in the decades since Fermi's lunch question. Because the scientific picture has changed significantly since 1950. We know things now that Fermi and Drake did not know. We know how common planets are. We know something about the conditions under which life arises on Earth and when. We know more about the range of environments in which life can exist. And what we have learned, mostly, has made the paradox harder to resolve rather than easier. The universe is not a sparse and inhospitable place. It is a dense, ancient, chemical-rich environment that, by most measures, appears to be exactly the kind of place where life should be abundant. One of the most significant developments in astronomy since Drake's time has been the discovery of exoplanets, planets orbiting stars other than our own. The discovery of the first confirmed exoplanet orbiting a Sun-like star, in 1995, opened a new field of astronomy. In the decades since, thousands of exoplanets have been confirmed, and statistical analysis of the data suggests that planets are not rare, they are, in fact, the norm. Most stars appear to have planetary systems. Many of those systems include planets in the habitable zone, the range of orbital distances at which liquid water can exist on a planet's surface. The Kepler Space Telescope, which observed more than 150,000 stars for 4 years, found that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. 1 in 5. In a galaxy of 100 billion stars, that implies billions of potentially habitable worlds in the Milky Way alone. Billions of potentially habitable worlds. In one galaxy. In a universe with 2 trillion galaxies. The numbers are, if anything, more extreme than Fermi's rough calculation implied. The universe is not just old and large, it is apparently full of the physical conditions that, on Earth, produced life. The question of how life arose on Earth and how likely that process is to occur elsewhere is one of the most important and most uncertain factors in the Fermi paradox. Life on Earth arose remarkably quickly, in geological terms. The Earth is approximately 4.6 billion years old. The earliest evidence of life, microbial fossils and chemical signatures, dates to approximately 3.5 to 3.8 billion years ago. This means life appeared within the first billion years of the planet's history, during a period when the Earth was still being heavily bombarded by asteroids. The rapid appearance of life on Earth has been interpreted in 2 contradictory ways. Optimists argue that life arose quickly because it is easy, that the chemistry of life is an inevitable consequence of the chemistry of the universe, that wherever the right conditions exist, life will appear. On this view, the universe is full of microbial life. Pessimists argue that the rapid appearance of life on Earth could be a survivor bias effect, that we observe life arising quickly on Earth precisely because we are here to observe it, and that planets on which life did not arise quickly are planets we are not on. On this view, the rapid origin of life tells us nothing about how rare or common the process is elsewhere. The chemical components of life, amino acids, nucleotides, the building blocks of proteins and DNA, have been found in meteorites, in interstellar clouds, in comets. The raw materials for life appear to be common in the universe. Whether the specific process of assembling those materials into self-replicating chemistry is easy or fantastically improbable is unknown. Even if microbial life is common in the universe, the transition from microbial life to complex multicellular life may be extraordinarily rare. On Earth, microbial life existed for approximately 2 billion years, from the origin of life around 3.5 billion years ago to the Cambrian explosion around 540 million years ago, before the proliferation of complex multicellular organisms. That is 2 billion years of a planet covered in bacteria, making almost no progress toward complexity. The specific biological events that allowed the transition to complexity may be extremely rare. The endosymbiotic theory of the origin of eukaryotic cells, the complex cells that make up all animals, plants, and fungi, proposes that this transition required one bacterial cell to be engulfed by another and to survive as an organelle rather than being digested. This event, which gave eukaryotic cells their mitochondria, may have happened only once in the history of Earth life. On another planet, it might never happen. Similarly, the origin of sexual reproduction, of multicellularity, of nervous systems, of intelligence, each of these transitions may represent a step that is not inevitable, that requires specific conditions or specific chance events, and that many life-bearing planets might never make. On this view, the rare Earth hypothesis, developed most fully by the paleontologist Peter Ward and the astronomer Joe Kirschvink, microbial life may be common in the universe, but complex life is rare, and intelligent life is rarer still, possibly unique. Even if intelligent life is rare, the age of the galaxy makes the silence puzzling. The Milky Way is approximately 13.6 billion years old, almost as old as the universe. Stars formed throughout this period, with the rate of star formation highest in the early universe and declining over time. Many stars that formed in the galaxy's first few billion years are still burning today, stars with longer lifespans than our Sun, around which planets formed billions of years before Earth existed. If intelligent life arose on even one planet orbiting one of these older stars, a planet that formed, say, 6 billion years ago, giving it 2 billion more years of habitable conditions than Earth, that civilization would have had 2 billion extra years of development. 2 billion years is an almost incomprehensible head start. What could a civilization do with 2 billion years? If technological development continues at any pace at all, a civilization with a 2 billion year head start should have capabilities that are essentially magical from our current perspective. It should have had time to spread across the galaxy, to modify stars, to leave marks on the cosmos that we could not miss. And yet we see nothing. This is why the Fermi Paradox is sometimes called the Great Filter Problem, not just where is everybody, but what happened to everybody? The absence of evidence for ancient, galaxy-spanning civilizations implies that something stops civilizations from reaching that stage. Something filters them out. And the question of where that filter is, in our past or in our future, is one of the most consequential questions we can ask. One of the most striking aspects of the Fermi paradox is that the absence of evidence is not just absence of radio signals, it is absence of physical colonization. The Milky Way galaxy is approximately 100,000 light-years across. A civilization with the technology to travel at even 1% of the speed of light, a technology that is challenging but not obviously impossible, would take approximately 10 million years to cross the galaxy. 10 million years sounds like a long time, but it is less than 0.1% of the galaxy's age. Even with slower speeds of travel, a civilization that began colonizing the galaxy in earnest would, given the galaxy's age, have had time to reach every star system many times over. The mathematician John Hart calculated in 1975 that a civilization colonizing at even very modest speeds would permeate the entire galaxy within a few hundred million years. A few hundred million years. The galaxy is 13 billion years old. There should have been, on this reasoning, dozens of opportunities for a civilization to have colonized the entire galaxy before we arrived. We are not in a colonized galaxy. There are no alien bases on the Moon, no alien artifacts in our solar system that we have found, no alien presence in our astronomical observations. The galaxy is not just radio quiet. It appears to be physically unoccupied except by us. The observational record of the search for extraterrestrial intelligence contains a handful of anomalous signals that have been investigated seriously and not explained. The most famous is the WOW signal of 1977, which we have discussed in another episode. It remains unexplained and undetected again. Its characteristics match what would be expected from an extraterrestrial radio transmission, and no natural or artificial terrestrial explanation has been found. More recently, in 2015, astronomers observed unusual dimming patterns in the light from a star called KIC 8462852, Tabby's star, that were inconsistent with any known natural phenomenon and that were briefly interpreted as possibly indicating a megastructure, a large artificial construction in orbit around the star. Subsequent observation has produced more mundane explanations, likely dust clouds, but the initial anomaly attracted significant attention. In 2017, a cigar-shaped object designated Oumuamua passed through our solar system, the first confirmed interstellar object ever observed. Its physical properties were unusual in several respects, and the physicist Avi Loeb of Harvard argued publicly that they were consistent with an artificial origin, a probe or a piece of technology from another civilization. Most astronomers have found natural explanations more plausible, but the debate has not been fully resolved. These anomalies do not confirm the existence of extraterrestrial intelligence. But they illustrate that the search is ongoing and that the universe occasionally produces signals and objects that require explanation. The numbers are real. Billions of potentially habitable planets. Billions of years of time. The apparent inevitability of life's chemistry, and the apparent rarity of its complexity. The mathematical certainty that a civilization with a head start should have colonized everything by now. And silence. In Part 3, we go through the solutions that have been proposed, the most serious attempts to explain why the universe appears to be empty despite the mathematics that says it should not be. Rest here. The sky is still there. 2 trillion galaxies. Silence. The solutions. There are many proposed solutions to the Fermi Paradox. They range from the reassuring to the terrifying, from the scientifically rigorous to the highly speculative, from the ones that say we are essentially alone to the ones that say we are surrounded by civilizations that are simply not talking to us. Each solution makes specific assumptions about the nature of life, the nature of intelligence, the nature of technology, and the nature of the universe. I want to go through the most significant proposed solutions systematically, not to adjudicate between them, because the evidence does not allow that, but to understand what each one implies and what it requires us to believe. The simplest solution to the Fermi paradox is that we are alone, that intelligent life is so rare that, despite the size of the universe, we are the only example. This is the rare Earth hypothesis, which argues that the specific combination of factors that allowed complex life to develop on Earth, the right kind of star, the right orbital distance, the right planetary composition, the stabilizing influence of a large moon, the right geological activity, the right timing relative to the galaxy's metallicity, is so improbable that it may have occurred only once, or only very rarely. On this view, there is no paradox. The universe is silent because it is empty. We are not one among many civilizations, we are, at least within the observable universe, the only one. This is a psychologically difficult position to hold. It places us at the center of the cosmos in a way that the history of science has repeatedly moved us away from. Copernicus told us we were not at the center of the solar system. Darwin told us we were not specially created. The rare Earth hypothesis would tell us that we are, in fact, cosmically special, that our existence is not representative of the universe's potential for life but an exception to it. It is also, from a scientific perspective, a position that is difficult to evaluate. We have one data point, Earth, and we do not know how representative that data point is of the universe's possibilities. A less dramatic solution proposes that intelligent civilizations exist but are too far away to have made contact. The universe is very large, and the speed of light is a limit on communication. A civilization 1,000 light-years away can only have received radio signals that we transmitted 1,000 years ago, before we were transmitting anything. The time for communication across interstellar distances is itself a significant barrier. On this view, the galaxy may contain many civilizations that are simply too far apart and too young, relative to each other, for contact to have occurred. We are all in our early periods, separated by distances that light takes thousands or millions of years to cross, and the probability that any two civilizations are close enough and old enough relative to each other to have made contact is very low. This solution is more plausible for a relatively young galaxy, one in which civilizations have not had time to spread. But as we noted in Part 2, the galaxy is very old, and a sufficiently advanced civilization should have had time to spread across it physically, not just send radio signals. The distance argument explains radio silence but does not explain physical absence. Several proposed solutions suggest that extraterrestrial civilizations exist but are not transmitting signals that we can detect. One version of this argument holds that advanced civilizations have moved beyond radio communication, that radio is a primitive technology used only briefly before being replaced by more efficient methods that do not produce detectable signals. On this view, we are looking for horse-drawn carriages in an age of teleportation. Our search methodology is simply wrong for the signals being sent. Another version holds that civilizations choose not to transmit, that an awareness of the potential dangers of broadcasting one's existence leads advanced civilizations to go radio quiet. This is the dark forest hypothesis, which we will examine in more detail in Part 4. A third version holds that we are too primitive to recognize their signals, that the communications of advanced civilizations are so compressed, so efficient, so technically sophisticated, that they are indistinguishable from noise to our receivers. We may be swimming in alien signals without knowing it. These solutions are difficult to evaluate precisely because they propose that we would not detect what we are looking for. They are, in a sense, unfalsifiable. If we find nothing, it is consistent with these solutions. If we find something, it would be a refutation of the "we can't detect it" version but not the "they're not transmitting" version. Some proposed solutions suggest that extraterrestrial civilizations exist and are aware of us but have chosen not to contact us. The zoo hypothesis proposes that advanced civilizations have made the decision, perhaps collectively, perhaps through some galactic equivalent of a prime directive, not to interfere with developing civilizations. Earth is being observed, possibly from a long distance, but the observers have chosen not to make contact. We are in a cosmic zoo, watched but not visited. The planetarium hypothesis is a more extreme version of this idea. The universe that we perceive is not the real universe but a simulation, or a carefully constructed environment, that prevents us from seeing the true nature of the cosmos. We are in a planetarium, and what we observe as the empty universe is a constructed display. These solutions share a common feature: they propose a level of coordination and restraint among advanced civilizations that seems, from a human perspective, implausible. Why would every civilization in the universe, including the ones that predate us by billions of years and have had time to colonize everything, agree to leave us alone? The level of consensus required for a universal zoo policy is extraordinary. Unless, of course, there is only one civilization old enough and powerful enough to enforce such a policy. Which brings us to a very different kind of proposed solution. The Great Filter is the most significant and most disturbing of the proposed solutions to the Fermi Paradox. The concept was developed by the economist Robin Hanson in 1998. The argument is this: the fact that we see no evidence of other advanced civilizations implies that there is, somewhere in the history of a civilization's development, a filter, a barrier so formidable that almost nothing gets through it. Some step in the progression from simple chemistry to galaxy-spanning civilization is almost impossibly difficult, and almost every potential civilization fails at that step. The crucial question is, where is the filter? If the filter is behind us, if the step that almost never happens is one we have already passed, then we are the lucky ones, the exceptional survivors of a barrier that has stopped everyone else. The most likely candidate for a behind-us filter is the origin of life itself, or the transition to eukaryotic cells, or the development of complex multicellular life. If any of these is the filter, we can relax, we have survived it. If the filter is ahead of us, if the step that almost never happens is one we have not yet reached, then the silence of the universe is not evidence of our exceptional good luck. It is a warning. Almost every civilization that has reached our level of development has subsequently failed to progress further. And we are approaching the same threshold. What might a future filter look like? Nuclear war. Engineered pandemics. Climate catastrophe. The development of artificial intelligence that is not aligned with human values. Any technology capable of civilization-ending destruction that all or nearly all civilizations have failed to navigate. Robin Hanson's analysis produces a disturbing implication: we should hope that life and intelligence are rare. If, in our search for extraterrestrial life, we find microbial life on Mars, or under the ice of Europa, or in the atmosphere of Venus, if we find that life has arisen independently elsewhere in our solar system, this is evidence that the origin of life is not the filter. Life arises readily. The filter is not behind us. If we find that complex multicellular life has arisen elsewhere, on an exoplanet, in some future observation, this is evidence that the filter is not the transition to complexity. That transition is not impossibly difficult. The filter is somewhere ahead. The more common life turns out to be, the more we find that the universe is full of microbes and even complex organisms, the closer the filter must be to us. The more we learn that we are not exceptional in our biology, the more exceptional our survival past the filter must be, and the more likely the filter is something we face rather than something we have already passed. This is a deeply counterintuitive conclusion. Finding extraterrestrial life would be, in this analysis, potentially the worst news humanity has ever received. The solutions are there. Rare earth. Too far. Not talking. Hiding. The filter. None of them is fully satisfying. Each one explains something and leaves something unexplained. Each one has implications for how we think about ourselves, for how we conduct our search, for how we think about our future. In Part 4, we go deeper into the most disturbing of these implications, into the dark forest hypothesis and the great filter, and into what the silence of the universe might be trying to tell us. Rest here. The solutions are laid out. The silence remains. The dark forest and the great filter. In 2008, a Chinese science fiction writer named Liu Cixin published a novel called The Dark Forest. It was the second volume of a trilogy that began with The Three-Body Problem, a book that had become one of the most celebrated science fiction novels in the world. The Dark Forest proposed a specific solution to the Fermi Paradox, one that was not new in its essential logic but that Liu expressed with a particular clarity and a particular darkness that made it impossible to ignore. The solution is this: the universe is silent because every civilization that broadcasts its existence is destroyed. The reasoning goes as follows. Resources in the universe are finite. Any sufficiently advanced civilization knows this. Any sufficiently advanced civilization also knows that the intentions of other civilizations cannot be trusted, that a civilization that appears peaceful today might become threatening tomorrow as its technology and needs evolve. In this situation, the rational strategy for any civilization that discovers another is to destroy it before it can grow powerful enough to be a threat. This creates a dynamic that Liu calls the dark forest, a universe full of hunters and prey, where every civilization hides, where any signal is an invitation to be destroyed, where the silence is not the silence of an empty universe but the silence of a universe full of armed, frightened civilizations pointing their weapons at anything that moves. On this view, the reason we have heard nothing is not that no one is out there. It is that everyone out there has learned, or is learning, to be quiet. And we have been shouting. The dark forest hypothesis rests on two axioms that Liu presents as foundational truths about any sufficiently complex civilization: the survival imperative and the uncertainty of other minds. The survival imperative is simple: any civilization, like any organism, has as its fundamental drive the continuation of its existence. Whatever else it values its own survival above all else, because without survival, no other value can be pursued. The uncertainty of other minds is more subtle. You cannot know, with certainty, what another civilization wants or intends. You can observe its behavior, but behavior can be deceiving. A civilization that appears benign may be hiding its true capabilities. A civilization that is currently peaceful may become aggressive as circumstances change. You cannot read another civilization's mind. From these two axioms, Liu derives the dark forest logic: if you encounter another civilization, and if you cannot be certain of its intentions, and if its survival could potentially threaten your survival, the rational choice is to destroy it before it can destroy you. This logic is cold and terrible, and it does not require malice. It requires only rationality, survival instinct, and the fundamental uncertainty of the universe. The dark forest is not populated by evil civilizations. It is populated by rational ones. The dark forest hypothesis is not purely speculative, it has some empirical support from what we observe, or fail to observe. The most striking piece of evidence is the wow signal. If the wow signal was a genuine extraterrestrial transmission, as its characteristics suggest, it was a brief, apparently one-time signal from a specific direction in space. It was never repeated, at least not in a way we have detected. Why would a civilization send one signal and then stop? One interpretation: they became aware that the signal was detectable, realized they had exposed themselves, and went silent. On the dark forest model, this is exactly what a civilization that had accidentally revealed itself would do. More broadly, the pattern of our search is a universe that appears radio quiet, whose civilizations, if they exist, are not broadcasting, is exactly the pattern you would expect in a dark forest universe. Everyone is hiding. The dark forest hypothesis also has implications for the silence beyond radio signals. If civilizations go dark to avoid detection, they would also suppress the physical evidence of their existence. They would not build megastructures, would not modify their stars, would not engage in the kind of large-scale engineering that would be visible to distant observers. They would hide. A universe in which everyone is hiding would look, from the outside, exactly like an empty universe. The Great Filter and the Dark Forest are not competing hypotheses, they can coexist, and the Dark Forest is, in a sense, a specific proposed mechanism for a future Great Filter. If the Dark Forest logic is correct, the filter that almost no civilization passes is the transition from a civilization that broadcasts its existence to a civilization that has been detected and destroyed by another. The filter is contact. On this view, every civilization that reaches a certain level of technological development, every civilization that starts broadcasting radio waves, as we did in the late 19th century, faces the risk of being detected and destroyed by an older, more powerful civilization that operates according to Dark Forest logic. The civilizations that survive are the ones that realize the danger quickly enough to go quiet. The ones that don't are eliminated. This is a filter that would produce exactly the universe we observe, radio quiet, physically empty of advanced civilizations, populated by civilizations that either haven't reached the broadcasting stage yet or have passed it and gone silent. And we, with our century of radio broadcasts now propagating in a sphere 100 light-years across, have already announced our presence. The Dark Forest hypothesis has direct implications for a debate that has been conducted among scientists and philosophers for decades, whether we should actively broadcast our presence to the universe. This debate, between SETI, the search for extraterrestrial intelligence, and METI, the messaging to extraterrestrial intelligence, turns on exactly the question that the Dark Forest raises. SETI is passive listening. METI is active transmission, sending deliberate messages into space in hopes of making contact. Several major METI projects have been conducted. The Arecibo message of 1974 was a brief binary encoded message broadcast toward a star cluster 25,000 light-years away. The Cosmic Call projects of 1999 and 2003 sent messages toward specific nearby stars. Various other transmissions have been made. The Dark Forest argument against METI is simple and disturbing. If the Dark Forest logic is correct, transmitting is an invitation to be destroyed. A civilization that has been broadcasting since the late 19th century, as we have been, may have already made an unintentional announcement. Deliberate, powerful METI transmissions would make that announcement louder and more precise. Against this, proponents of METI argue that our existing radio transmissions have already spread 100 light-years in all directions, that the ship has sailed, that anyone who is close enough to be a threat already knows we're here. Further transmission, they argue, is no additional risk. The debate has not been resolved. The scientists who have raised the strongest objections to METI, including Stephen Hawking, who repeatedly warned against contact with alien civilizations, are opposed by others who believe the potential benefits of contact outweigh the risks. Not all proposed solutions to the Fermi Paradox lead to dark conclusions. Some physicists and philosophers have argued that the filter is behind us, that we have already passed the hardest step, and that the silence reflects the rarity of our good luck rather than a warning about our future. If the origin of life, or the origin of complex life, or the origin of intelligence, is the filter, then the universe is full of planets that tried and failed to produce what Earth produced. We are the exception, and the silence is the sound of all the planets that didn't make it. On this view, the discovery that we are alone, or nearly alone, is not terrifying but remarkable. We are the universe's first attempt at intelligence, or one of its earliest. We are the explorers of an empty cosmos, with the responsibility and the opportunity that entails. Others have argued that the filter is not death but transcendence, that advanced civilizations eventually move to forms of existence that are not detectable by the methods we use, that they upload their consciousness to digital forms, or retreat to simulated environments, or undergo some other transformation that removes them from the physical universe as we know it. On this view, the universe is not empty but transformed, full of minds that have moved beyond the kind of existence we can observe. These optimistic solutions require no less faith than the dark forest. They are possibilities, not certainties. Go outside tonight, if you can. Find a dark place. Let your eyes adjust. Look up. 2 trillion galaxies. Hundreds of billions of stars in each one. Billions of years of time. An apparently infinite abundance of the conditions for life. And silence. The silence might mean we are alone, the first, or the only, intelligence in an empty cosmos, charged with the extraordinary and terrifying responsibility of being the universe's only witnesses to itself. The silence might mean we are in danger, that the cosmos is a dark forest, and that we have been singing too loudly for too long, and that something in the darkness has already heard us and is moving in our direction. The silence might mean something else entirely, something we have not yet thought of, something that requires a framework we have not yet developed, something that will seem obvious in 100 years and is invisible to us now. What we know is this: we are here. In a universe that might be empty or might be full, in a galaxy that is either the site of ancient civilizations or a pristine wilderness, on a planet that is either one of countless inhabited worlds or the only one, we are here. Thinking. Searching. Asking the question. The asking is not nothing. It may be everything. If we are alone, the asking is the universe asking itself. If we are not alone, the asking is the thing that distinguishes us from the silence, the refusal to be quiet, to be content with not knowing, to stop listening for the signal that has not yet come. The stars are there. The silence is there. And we are here, in the dark, listening. Good night.